Hello everyone, Assalamu alaikum. Welcome back for another video in the series. In this video, we shall learn to code logistic regression model using the concepts we learned previously. Keep in mind that the learning rule for logistic regression model is the same as has been discussed previously in Adaline. Yes, I'm talking about gradient descent algorithm. Links for the videos are provided in the description box. So let's just open our code notebook where I should implement two things. So the first thing is logistic regression from scratch, just from the ground up, low level implementation of logistic regression. It's really like implementing the learning rule that we talked about here. And then I will show you how we can do that using the PyTorch utilities, where we have this n dot linear layer and so forth. This is something we would do in practice when we have, of course, more complicated networks, but I thought from scratch implementation is still useful from a learning perspective, so you get a better feeling of how logistic regression works. So let's just get started. Now, starting off with the libraries, of course, we will be using some simple toy dataset. Let me show you. And that's just a simple binary classification dataset. Let me just quickly write the starter stuff that we have already talked about in the previous coding videos as well. The train and test split, set split, etc. Nothing new. Now let me write my logistic regression implementation, then we will discuss more. So how does this work? I'm using the roughly same way how we could implement this using PyTorch with the module API. So here I am implementing forward and backward manually. These are the two methods where forward is the forward pass and backward is the gradient descent computation. The gradients of loss function like. So that's the gradient of loss with respect to the output and so forth. Starting with the init function, the initialization one, this is like the function or method that gets executed when we initiate a new object from this class. What we have is the weights and the bias unit. So the weights, we initialize them to zeros, so we use the zeros function to initialize them. It's a row vector, basically a 1 times n number of features vector here. So our matrix, so it's essentially a row vector. The number of features is number of features in data set, so the number of weights is equal to number of features, and we only have one bias unit. So the forward method, this is computing the net input, right? So this is the net input. We can call it C. And in the backward method, it's computing these gradient terms. So here I'm computing the gradients of loss with respect to the output, then the gradient of loss with respect to the weight. So this is a matrix multiplication between x and this term. I just rearranged that to make the dimensions match, which is why I have the transpose. To be honest, we don't have to memorize these details. You will probably find out by tinkering with the code. If you ever implement something from scratch, because this is really for one weight, then we do the same for the bias. Here this is the threshold function, predict labels. So I'm calling forward, that gives me the probabilities. That's the sigmoid activation here, and this is the threshold function, where if the probabilities are greater than 0.5, return class label 1, otherwise return class label 0. Okay, now we just have an evaluation function here, in which I am predicting the labels, which in turn uses this method here, which computes forward, and then threshold function here. And then in order to compute the accuracy, we sum over the correct predictions. So every time the class label, that is the predictions, matches the actual class label, every time they match, we sum that up. So this is the number of correct predictions, and then we divide by the size of training set. So it's a value between 0 and 1. It's the proportion of correct predictions. Why I do a float here, it's because the class labels are integers, and in PyTorch it's a little tricky to compute or compare things like floats. The labels are floats here. And then this is the integer, So this is a sigmoid function which you have seen a lot of times. The loss function, that's the negative log likelihood, which we have right here at the bottom. That's the logistic cost function. And here's the training function. So for every training epoch, for e in the number of epochs, we compute the outputs. Then we compute the gradients, then we update the weights, and this is essentially it. So this is just for logging, just keeping track of everything, like looking at the results and loss curve, which can be useful. So let's actually run the model. What I'm doing is I'm converting the NumPy arrays to torch tensors. So to load the data, I'm just converting them to torch tensors. Then I'm initializing my logistic regression model. So this will be actually step 1, initializing, and then I'm calling train, and then I'm printing the model parameters, the weights, the bias, just to take a look at them. And I'm training for 30 epochs while with a learning rate of 0.5. Let's execute this code and see what happens. Okay, now we are running the code. So it's training, you can see it's blazing fast, starts with already a very high accuracy after the first epoch, to be honest. So it's actually training super fast. The cost is very low, but you can see it goes even lower. The accuracy goes up to 100% here, but you can see even though the training accuracy already 100%, the loss still goes down. I could have trained more and would go maybe further down, but that at that point might not be necessary. It might be overfitting. Now let's plot the model. So you can see here is how the negative log likelihood loss looks like. So it should be the negative log likelihood loss, to be precise, and then over the number of epochs you can see maybe it will go down further. You can see it's actually going steep down, but whether it's actually helping, it's I don't know, because we already get 100% training accuracy. So let's take a look at the test accuracy. As you can see, it's only 96%. Now for completeness, we will also take a look at the decision boundary. So we can see actually here on the training set, the decision model looks quite good. So it's dividing both classes, class 0 and class 1. On the test set, it's not performing so well because there's this one outlier point. So here this one is not classified correctly. So if this decision boundary would go a little bit more to the right, then we might get this one correct, because at this point this model only sees the training data, doesn't know if of this point here on the right hand side. So this in this case, I think training the model further wouldn't really help, because this is really doing a good job here. Keep in mind that this is a toy data set anyway, so don't overinterpret this. So the goal here was really to show you how we implement this from scratch. Now I want to show you how we use the module API to implement this logistic regression model. So here this should do exactly the same thing, but now I'm relying on inbuilt or built-in PyTorch functions. So I'm using this self.linear here to refer to my torch.n.linear layer. This is a layer that computes the net input. However, note that by default this will initialize the weights to small random numbers. Later on this will be very useful, but it is not that useful to compare to our model, because if you recall above, I initialized my weights and bias to 0. So I want to do the same thing here, so I can compare the two models. So what I'm doing is manually assigning zeros to the weights and bias unit. And then we have the forward method. So here the forward method, we compute the logits via the self.linear, which is this fully connected layer or linear layer. And then we have built-in PyTorch function that compares or computes the sigmoid activation function. So you can see a logistic regression model is actually super simple, and it will already implement the backward function for us. We don't have to do it ourselves. Here we are using the stochastic gradient descent optimizer, and this will update the weights then. So this will compute the gradients via the backward and update the weights. So we are just specifying the what weights we want to train. This is the model parameters here, model 2, right? So just write an accuracy function to compute the prediction accuracy. We are training also for 30 epochs like before. What I'm doing is I'm casting the numpy on a raster tensor. I've already done that, so it's pretty redundant. And now here's my training loop in PyTorch. So for each epoch I compute the outputs. These are the probabilities. This is from the forward pass. This is these probabilities here. Then I use this cross entropy, binary cross entropy function here. The negative log likelihood and binary cross entropy are essentially equivalent, so you don't have to worry about that. Same thing, I'm saying a reduction sum because that's what we have done here. It's the sum, or we can also do the average. In practice, I think using the mean is more stable for with regard to learning rates and different batch sizes. And then this is really like what we have done in a previous video. We learned to use where we learned to use this Autograd function. We have the following: we compute the loss, and then we set the optimizer 0 grad, which will reset the gradients from previous round. Otherwise the gradients will accumulate, like I explained before in the previous video. And then we compute the gradients for current round and then update the weights, and this is essentially it. Okay, so you can see, if you recall, these have the same values as we have seen before. So we already so we learned exactly the same using PyTorch, which gives us confidence, because I hope that we understand gradient descent correctly and implement the gradient here correctly. So it's the same as in PyTorch. That is it. Now that's it essentially. So evaluating the model, same test accuracy because it's the same weights and bias, so it should be the same decision boundary, which we can see here. So this is how we implement logistic regression. I hope that this was helpful, like I understanding a little bit better how these different concepts here in the slides work. You may also want to work through this more slowly. I think that this might be helpful, but that is essentially it. If you have any questions, drop them in the comment box below, and I'll see you in the next video.